Okay, so here's where we're picking up. You might recall last time we were talking about vector surface integrals. Flux, right? So the motivating physical application that we think of when we think of vector surface integrals is flux. So the vector field we think of as representing a fluid. So forget about forces, right? No forces. Thinking about fluid flowing through space. And if we have a surface that we think of as kind of a net that the fluid might flow through. And if we have a fluid that's flowing to some extent, in some way through the net, reasonable question would be how much volume, total volume per unit time of that fluid is passing through the net. Okay. All right. So we write it down, formulas, Riemann sum, all that business. Okay. So what I want to talk about now, we saw some applications or some examples last time. I want to talk about how similar this is to the vector line integral construction that we talked about in the previous section. Now remember, the vector line integral construction, totally different motivation. The motivation had nothing to do with fluids. Right? With vector line integrals, we were talking about the vector field as representing forces. And we were interested in the question of how much work would it take to move and, applying forces while moving along a certain curve. So work and forces as opposed to flow rates and flow fields. Completely different applications. What's weird is how much these constructions have to do with each other mathematically. So anyway, so here's a little comparison I like to do between these. I'm drawing the parameterizations here. In a weird way, I'm drawing them vertically instead of horizontally, and that's just for typographical reasons. It's just the paper isn't wide enough for me to fit it all, horizontally, and I wanted to have a left-right comparison. So here we are. So anyway, but these are just parameterizations, domain, target, the usual way. Okay. All right. So we have these two parameterizations. In each case, here we're moving along a curve, parameterizing a curve. Here we're parameterizing a surface. Right? In each case, we can talk about certain vectors that tell us about the orientation of the curve. So when we talk about the orientation of a piece of curve, we're talking about what direction is the curve going. Right? What's the unit tangent vector? Whereas when you're talking about a piece of surface at a given point, there's lots of tangent vectors, but the thing that defines the way the single vector that helps you define the way a piece of surface is oriented is a normal vector. Right? So something perpendicular to the surface tells you how to arrange the surface. Okay, fine. In both cases, we compute that by way of a vector that comes from derivatives of the parameterization. In the case of line integrals, we're looking at the derivative, right? Velocity vector, which points in the direction of the tangent vector. In the case of surface integrals, we're talking about this capital N, which doesn't look like a derivative, but remember where it comes from. It's xu cross xv, those vectors participating in the cross product being derivatives. They're partial derivatives, right? So it's a variation. But still, it comes from derivatives of the parameterization. Okay, so capital N is kind of analogous to x prime, kind of analogous to v, you might call it, in that it's a derivative of the parameterization that points in the direction that defines the orientation of that piece of the domain. Yeah, weird. What a coincidence. Okay. Let's see. In both cases, we're interested in the size of the little piece of the domain here. Let me. What I was already. Okay, so we're interested in, for example, on a line integral, we're interested in the length there of the piece of curve. Over here, with a vector surface integral, we're interested in the area of that piece of surface. And in both cases, we can talk about this related vector, so the dx vector, the ds vector over here, that play, again, analogous roles. Both of these vectors, by way of the direction they point, tell you about the orientation of that piece of the domain. And both of these vectors, by way of their magnitudes, tell you about the size of that piece of the domain. So, length over here, area over here, but still size in both cases. Okay. So then now let's look at how the constructions themselves go together. You can see that these things, even in the way, all these algebraic relations that we have written down here, this is a bunch of stuff about vector line integrals. This is a bunch of stuff about vector surface integrals. Nothing on the page is new. These are all things we've written down previously. But look how strong the analogies are and how these things relate to each other. So, the unit vectors that you multiply by sizes give you your domain differentials. So your position differential here, your surface differential there. Both of these are computed by way of derivatives multiplied by parameter differentials. Right, the analogy is very strong. We're doing the same thing with surface integrals that we were doing with line integrals. Didn't think that way when we wrote it down in the first place, but it's highly analogous. Along these same lines, notice that let's see, I'll do it like this, that the magnitudes play out in very similar ways. Right, the analogy being that, the magnitude of x prime, magnitude of x prime there, magnitude of n there, parameter differential there, parameter differentials there, size there, the analogy is basically perfect. Both of these kinds of integrals we can write in different forms. We talked about these various different forms for vector line integrals, for vector surface integrals. Note that in each case we're talking about accumulations. In each case there is a kind of a what I like to call my favorite notation. Namely, where we have the differential representing everything you need to know about the piece of domain, that curve or surface, represented as a single vector. In both cases, we can rewrite in terms of a parameterization. In both cases, you can rewrite in terms of dot products with unit vectors. These are the orientation unit vectors. In both cases, you can think of this as then computing a kind of what looks like a scalar integral. And this looks like a scalar line integral. This looks like a scalar surface integral. Of what in fact is just the corresponding component of your integrand. Okay? So the analogy is really very strong. They look a lot like each other mathematically. Okay, so it's kind of weird to notice this. Now let's ask the question of why. Is this a coincidence? What are the odds that everything would just line up like this? And the answer is not a coincidence. This is, I picked these two particular applications, work and flux, because they would give rise to these two particular constructions which have so many things in common. But the question remains, why do these constructions have so many things in common? And the answer is, they are both special cases of a single, larger, more sort of all-encompassing general construction. They're both special cases of the same thing. So, no surprise if you look at special cases, examples of if you take one thing and look at two different examples of it, they're going to have a lot in common. Right? So no surprise there. So briefly then, what is it that vector line integrals and vector surface integrals are examples of? And so the answer to this question is that I cannot tell you the answer to that question in Math 212. It's a little too sophisticated, a little too deep. But roughly speaking, we're talking about integrals of differential forms, is what they're called. And you can talk about differential forms in a variety of different contexts, not just two-dimensional and three-dimensional, but as many dimensions as you want in whatever context you want. And it turns out is a very, very powerful construction. Differential forms in general. So anyway, there's more we're going to say about differential forms. But I'm never really going to tell you exactly what they are, other than to say that this is the tip of the iceberg. This is the great many coincidences that we're going to observe from here going forward in the rest of this course. Those coincidences happen because, well, we're looking at different examples of the same general construction. So anyway, just wanted you to know, very, very broadly and roughly why that is. We talked about flux through a surface. Next idea is flux through a curve. This is a very, very similar idea. Instead of having a surface, right, through which a three-dimensional fluid is flowing, if you have just a curve, did I draw a picture here? Yeah, if you have just a curve, this is just a curve in the plane, right? You could reasonably ask if you had a two-dimensional fluid flowing in some way. You could ask how much two-dimensional fluid is flowing through this one-dimensional curve. Totally analogous. I'm going to let you all read this subsection for details. It's pretty straightforward and very analogous ideas. Okay. All right, it's very short. Okay, so moving along. This is the last new kind of integral we're going to talk about, and arguably it's two new kinds of integrals, I guess, depending on, anyway, let's just say two. Let's count how many do we have going in here. Single variable, double integrals, triple integrals. Scalar surface integrals. Let me do it like this. Scalar surface integrals, scalar line integrals, scalar surface integrals. Vector line integrals, vector surface integrals. And now we're going to do two more. Our current total of 7 will therefore come up to 9 different kinds of integrals. All right. So these are called, I like to call them coordinate line integrals and coordinate surface integrals. This is going to come from considering a little bit of algebraic games. Make an observation here of something we've already done. We've already motivated vector line integrals. We know that dx is x prime dt. Yawn. Right, that's not news. And we know that x prime, well, that's just a derivative of this vector valued function. We know that derivative is taken component-wise, and I know that I can rewrite that like this. So this x prime I can plug into there, and I get this. Right? I haven't really done anything new yet. I'm just sort of fleshing out constructions we already have. I can think of my dx vector as being made up of, having these three components. Okay, so here's the thing. Now let's look at one of these. Let's look at that first component. I really want to call that dx. Right? The dx scalar. Why do I want to call that dx scalar? Well, come on, look at the dt's. You really want to cancel those dt's, and in fact, that's basically fine. Right? Because we know what's going on here. We know what the picture is there. If we have a dx vector, right? If our curve is cruising along like this, then our dx vector, there's our dx vector. That represents displacement. And displacement means you're changing in 3 different coordinates, those being dx, dy, and dz. I mean, we already kind of know this is going to be the answer. So what should I call the first coordinate of the displacement? Well, the first coordinate of the displacement represents how much did the first coordinate change. So d of that first coordinate, it just begs to be called dx. Okay. All right. Doing that, I'm going to skip a bit and come back to it. Notice if we make that very reasonable choice, now we have a way to describe the dx vector in components. We've never really done this before. We haven't written down the components of dx. We've just written it as v dt, and then you do the dot products. So that's detailed. That happens later. We never really fleshed that out. But reasonable, we see now, to call it the dx vector, dx, dy, dz. Don't forget our vector field. We also have a kind of a convention that it has components p, q, and r. And now, having written it like this, notice we can talk about what would happen if you write out one coordinate at a time, all the terms from that dot product. And what you get is that our vector line integral, we want to write it like that. Except the, minor little annoyance that we have yet to define what that means. Right? We never have written down what it means to take an integral over a curve of a function dx. Right? And we've talked about integral over a curve ds. This is not ds, this is dx. It's different. Right? Don't think of this as a density times a size. That's not what this is. Dx is not a size. It's a change in a single coordinate. Different. Now, we've talked about an integral over a curve of something dx, but that was the dx vector, and we were doing a dot product. That's not what this is either. It's just a different construction. It's a brand new construction. Now, in some sense, given what I have to mean by this, I have to mean, when I write this down, by this dx, I have to mean, like I wrote previously, dx dt times dt. Right? So all this is sort of a notational alternative, and so here's the definition down here. If you want to write down an integral, these are called coordinate line integrals. Coordinates because we're looking at differentials of coordinates, and line integrals because the domains are curves, like all the other line integrals we've talked about. Right? So when you write down one of these coordinate line integrals, all you mean by dx is, well, it's just x prime dt, exactly like you were expecting. What do you mean by dz? Well, it's z prime dt, just what you sort of assume it would be. That's all it is. And all it does is it gives us a sort of a notational alternative, sort of a different way to write, this. Instead of writing a vector line integral like that, you can instead write a vector line integral like this. Okay. Unimpressed? Rhetorical question. What does this help us compute? Not really anything. If you think about it, how would you go about computing, this thing here? Well, the way you'd go about computing the sum of three such things, p dx plus q dy plus r dz, the way you compute the sum of those things is by, you'd compute the sum of these things in which you can explicitly see, there's your vector field, there's your velocity vector. You can explicitly see f dot v dt. It is not computationally different. This is not a computational convenience or anything. It's just a notational alternative. So that brings up the question, okay, well, if this doesn't help us compute things, why would we write it down at all? Right? Why are we here? Why are we talking about this? So there's two reasons I'm telling you about this. One is this notation is popular. A lot of people like this notation. Second reason is that you may recall a few minutes ago I was talking about these abstract, sophisticated things called differential forms and integrals of differential forms, and it's this powerful, all-encompassing way of thinking about vector line integrals, vector surface integrals are all special cases. So it's this much more bulky, sophisticated, powerful way of doing all of that stuff all at once. And that's great. Integrals of differential forms look kind of like this. Right? This is, if you wanted to rewrite this as an integral of a differential form, it would look a lot like this. Right? So there are great reasons to want to use this notation. we are not going to see any of those great reasons in Matthew 12. Right? But those great reasons cause other people to want to use this notation in context that you are going to see in your engineering future or economics future or wherever you're studying. This notation is out there pretty significantly. So what you have to realize that when you see something like this, right, just remember, okay, well, all right, that's that weird coordinate alternative to representing that. Right? So if you see this out there, then look, okay, fine. Look, the dx, the dy, and the dz, that's just a fancy way of saying dx vector. And whatever these integrands are, the p, the q, and the r, corresponding to how they're paired up with the dx, the dy, and the dz, that's just representing the vector field of which I'm doing a vector line. Right, so I would encourage you, anytime you see this notation, think, okay, maybe yes. Just think of it in these terms, because I feel like this is more physically relatable. You can see the vector field. You can see the position differential. Very relatable to applications. Much more so, I think, than that. Okay. All right. Now, there is a surface version of this same story. I'm going to show you the surface version in a moment. I'm going to rewind just a bit, though, for a moment and talk about a different way to think about the dx scalar. Y'all already know what dx is. It's no big deal. Dx is, well, if you were here and then you were here, there's a change that happened, and it going from the blue point to the purple point, the x-coordinate changed by some amount. And by the way, the y-coordinate changed by some amount, and each of those you can call its own differential, and the change in x, how much did x change? We call dx. Okay, now, that's fine. It serves its purpose. I want to give you an alternative. For the same reasons that I give you all alternatives and lots of other things. Remember, there's lots of situations where you had a perfectly good way to think about a certain thing, and I say, well, let's think about it in this different way. And the reason was because it generalizes better to think about things differently. When we started talking about derivatives, right, I told you to jettison the idea of thinking of a derivative as a fraction, right, and a slope. And these are really useful in single variable calculus, less so in multivariable calculus. And I promoted this other idea of thinking of derivatives as input-output vector, a relationship between input vector and output vector. Okay, so likewise here, I want you to think of this in a different way. Here's what I want you to think of. As you move along a piece of curve, that piece of curve, if you were to project down to the x-axis, right? The shadow, if you will, of that piece of curve in the x-axis. Well, you have a little shadow there. There's a chunk of the x-axis. There's two things that you can say about that chunk of the x-axis, that shadow. One is, how big is it? And the other is, which direction is it going? And what I mean by that is, look, when you had this piece of the curve, it was going a certain direction. This is an oriented curve, right? It's going that way. So just use your imagination. If it's going that way, then that suggests that its shadow is going that way. Right? So dx represents these two things. How big is the shadow and what direction is the shadow going? The magnitude of dx tells you how big the shadow is. The sign of dx tells you which direction it's going. So notice here, this little piece of curve here was going, that way. The shadow was whoops. Sorry, my elbow again. The shadow is going that way. That's the positive x direction. So dx is positive. Okay. Whereas, on the other hand, let's look at this other piece of curve over here. Here's another, moving along. The curve continues around, Right, here's the next piece of curve that I want to look at anyway. It's got a size. It's going a certain direction. That gives you a shadow. Here, let me do this in a different color for comparison purposes. Gives you a shadow. Right? Which is itself going a certain direction. In the sense that, well, if the curve was going that way, you imagine the process of taking a curve going in that direction, and as it shadows down, that suggests it's pointing this way, in this case. Which is not in the direction of the x-axis. It's the opposite of the direction of the x-axis. So again, both of these are encapsulated by what dx is. Dx has magnitude equal to the size of that projection and is negative, indicating that this piece of curve's shadow is going the opposite of the x direction. All right, so it's kind of a weird way to think about it. I mean, change is so much easier to relate to. Well, what was x? What is x now? How much did it change, right? It's this minus that. It's super easy. If it's negative, it means it's going backwards. Very relatable to think of it as change. That doesn't generalize very nicely to surface integrals. This will. I want you to think of, for any given piece of curve, dx says how big is the shadow, and did the projection happen the right way? Or did the projection happen what you might call the wrong way? All right. Okay, so let's do surface integrals. Same deal. I'm going to start off in the same direction as we had been. So remember, here's a surface integral, flux integral, right? ds in du dv, old news. We wrote that down a long time ago. This in is xu cross xv. And again, that's where we kind of left it. Xu cross xv, a little nice compact formula. Just kind of left it as it was. And then, of course, you actually execute the partials, you execute the cross product in individual examples, and you work stuff out. So I'm just pointing out here that just like we did in the case of line integrals, we could expand that out here. Here's what it looks like one coordinate at a time. Take the u partials of the parameterization. Here's the v partial. And you can crank out that cross product. When you crank out that cross product, you're going to get three components, each of which, recall how cross product works, each of which is a little 2x2, determinant, which we can denote using this notation. Yeah. Right. So the cross product. I'm just going to remind you how cross products go. I'll do the first part of this calculation. So we have xu, xv. Oh, sorry. Xu, yu, zu, and then xv, yv, zv, and then e1, e2, e3, and we take a determinant, symbolic determinant. That's how you do a cross product.
Oh yeah, just right? Why does go away?
Why does what?
Like you said that xu and xv, or I don't know which value you said going away.
I'm having trouble hearing you.
Like which value is going away?
Which value is going away?
Yeah, you said it's going
I'm still not 100% sure what you're asking me, but I'm just pointing out that when we have, xu cross xv, previously we just kind of left it in that format, form, and we only actually cranked out the cross product manually in specific examples. I mean, actually write the whole thing out.
I felt like it was like eliminating the values, so I don't know.
Okay, yeah. No worries. Yeah, so anyway, just you ask a great question. So let me show you where this first thing comes from. It comes from, well, we are in fact taking a cross product here, and this cross product is this cross product, and the first component is that times the determinant of that little 2x2 matrix, which gives us that using this notation. Yeah. Okay, so bunch of details there that we've finally gotten around to writing down. It was kind of all implicit previously, and now let me just observe. That being a formula for my n vector. Multiplying by du dv. There's my n du dv. So this is, my ds vector. I've got this big formula for my ds vector. Right? Let me remind you, when we were talking about vector line integrals, we had an explicit formula for our dx vector, which caused us to ask, what can I call that? And we decided to call it dx. Right? We're in the same scenario now here with surface integrals. Here is our ds vector. What am I going to call that? And again, there's this temptation. You look at the notation, you're like, oh, come on, you just really want to cancel the du dv with the partial uv in the denominator there. It just begs to be canceled. But we don't really have this isn't a change, right? So this doesn't, I can't just say, oh, come on, it's obviously dx. This is not a previously familiar scenario. So it is not immediately obvious what I'm going to do with that or what I can do with that. But it turns out that we can actually reinterpret that very naturally. We just have to look at it in just the right way. Okay. And for artistic convenience, I'm going to look at the third coordinate instead of the first coordinate. The arguments that I'm about to give apply equally for all three of them. You just have to, look in the three different coordinate planes. I'm going to focus on this one because that's where I have my existing drawings already drawn. But it'd be a great exercise for you guys. Take the argument that we're about to give for this coordinate, think it through. How would you apply that to the other two coordinates? Okay. All right. You see this notation here. Partial xy, partial uv. Where did we previously use this notation? We used that previously in thinking about stretching factors for change of variables functions. So this kind of suggests, or at least makes us curious, can I think of x and y as being functions of u and v? Am I doing a change of variables between the uv plane and the xy plane? And the first thing that you think is, well, no, I'm not. I've got a piece of surface here. We're not in R2, we're in R3. And it feels like we're not doing a change of variables. But in fact, in a way, we kind of are. I claim x and y are functions of u and v. And here's how. Here's my little piece of surface in the x, y, z space. A little piece of surface there. But keep in mind, that's not just a piece of surface. That piece of surface here, I've parametrized. So that's the image of a little rectangle over here, and I parameterize my surfaces in terms of u and v. So, in fact, we have, indeed, x, y, and z as functions of u and v. Now, okay, that's not, that doesn't tell me what I want. I mean, what I'm looking at here is I need to be looking specifically and only at x and y as functions of u and v. I've got too many variables, but I need just x and y in terms of u and v. I have, unfortunately, x, y, and z. Okay, so how can I view just x and y? I would like to throw away the z-coordinate. I wish the z-coordinate wasn't there at all. Let's just get rid of, let's just, kill the z-coordinate. Let's just have it go away. And if you think about it, if you're in 3 space and you just throw away the z-coordinate, what you're doing is a projection. Right? You were taking a point here, x, comma, y, comma, z, and you're taking instead just x, comma, y. And now, in fact, we really do have, literally, x and y as functions of u and v. Okay, so this was here all along. We just weren't looking at it exactly the right way. The way we see how x and y are functions of u and v is that whatever piece of surface we're interested in, whatever piece of surface that was parameterized by way of u and v, take that piece of surface, look at its shadow in the xy plane. The act of looking at its shadow gives you exactly what you need, x and y, in terms of u and v. And so said differently, this thing here, this little fraction-looking thing here that I really want to think of as a stretching factor. It is a stretching factor. This is a stretching factor that's telling you about the proportions between this input area there, the UV rectangle, and this output area, the area of the projection, not the original piece of surface, but the area of the projection of that piece of surface down into the XY plane. Yeah? Everybody good? So, yeah. This construction, stretching factor times du dv. Du dv was area in the UV plane multiplied by a stretching factor. This is the area in the XY plane. This thing that I'm trying to figure out what to call it, this thing, partial xy, partial uv, du dv, is this area. Well, its absolute value is that area. That's really analogous to what we saw back with the line integrals. Let's go back to line integrals here. And, I had this seemingly unnecessarily awkward point of view about how to think about dx. Take your piece of curve. What's the size of the projection? Right? How big is the projection down to the x-axis? That's what dx is. How big is the projection to the x-axis? Well, what we have here is that thing is how big is the projection, not to the x-axis, but the projection into the xy plane. Okay, and as such, you're going to want to call this, for visual convenience, let me put that there, what you're going to want to call this thing is dx dy. Seem like a reasonable choice? So anyway, this is, the geometric motivation for it is that the thing that we're trying to figure out what to do with, in fact, it very literally represents, I'm going to ignore the absolute values, it represents an area in the xy plane. Areas in the xy plane we want to call dx dy. Also, again, we keep wanting to do that, which also suggests wanting to call it dx dy. So, pretty darn reasonable choice to call that dx dy. Okay, so that's the choice that we make. Here it is. So, dx dy is the name we give to that thing. Analogously, and I want you all to work these out for yourselves, just think them through in the same way that we just did. That thing we'll call dy dz. And this thing we'll call dz dx. By the way, do be careful of one little detail. It always seems confusing, but you have to write this as dz dx. You cannot switch the orders and call it dx dz, because if you look very carefully at how this is defined, it's defined by way of this, which is a determinant. It's a determinant specifically. If you say, well, I'd like to change, I want to write dx dz, I just want to put things in alphabetical order, it feels more natural, or whatever. If you do that, then you're switching these, which means you're switching these, and in fact, you will get the negative of what you otherwise would have gotten. And that changes things. So you have to leave it as dz dx. It is not the same as dx dz. Okay, so with that in mind, Here's where we were. And I'm going to go back and talk about the pluses and minuses in just a moment. But recall, this is where we got stumped. Right? We were able to rewrite the ds vector. Just expanding things algebraically, we had ds written as this. We find ourselves stumped with, well, what am I going to do with this expression here? We just agreed that dx dy is a reasonable thing to call it, and likewise, that's dy dz, and likewise, that's dz dx. And so what we have is, it's a bunch of effort to go to write it all down, but what we have is a very convenient way to think about the ds vector. Our vector differential, our surface differential, you might call it, has components which are coordinate differentials. And just like we did in the previous case, that combined with the fact that f has components like that, p, q, and r, suggests rewriting flux integrals as these things. And again, these are brand new kinds of integrals that we've never written down previously because, well, I mean, they're surface integrals, but they're not scalar surface integrals because dy dz is not ds. It's the area of the projection of ds. It's not ds itself, right? Likewise, this is not the ds vector. I mean, it's just a different thing. This is just a coordinate differential instead of a area differential or a vector differential. Okay. Yeah. So very quickly, I want to go back and talk about pluses and minuses. What does it mean if this thing is positive versus negative? Right, so we already agreed that the absolute value of this thing, the absolute value gives us the area of the little piece of projection. Well, I claim that when this thing is positive, what that means is that the surface with its normal vector, and it might be, how it's tilted exactly, I don't know exactly, but the surface with its normal vector, when you project it, it projects roughly right side up. On the other hand, if this thing is negative, what that means is this little piece of surface projected, I don't know exactly how it's oriented, but in some sense it projected upside down. So why upside down? Well, because this normal vector, this unit normal vector, is pointing somewhat down. It's not pointing generally up like this, it's pointing generally down. That's what's going to make it project upside down. Now, how do I know this thing is pointing down-ish? I claim that this vector has a negative third coordinate. How do I know this thing has a negative third coordinate? Because this is its third coordinate. If this thing is negative, right, then that means that the third coordinate of this vector is negative. That means it's pointing down. That means it's projecting upside down. So that's really just kind of a observation. Okay, so again, why do we use this notation? I have to show you this notation because other people like it. Other people like it for two reasons. Other people like it for good reasons, namely, if you talk about differential two forms in 3 dimensions, this is what they look like. This is very close to this very natural but very sophisticated construction of integrals of differential forms. Very powerful point of view. Right? This isn't exactly it, but this is highly suggestive of what that looks like. So there's great reasons to want to use notations like this. Some people like this notation because they use it for those great reasons. Some people like this notation because they've seen other people do it and do great things with it, and therefore they just like this notation. I don't know. I think in the context of Math 212, it doesn't really make a lot of sense to use this notation. It's just a clunkier alternative to representing this. But just be aware that this is out there. You're going to see this notation outside of the context of Math 212. And just keep in mind that these differentials, written exactly as so, are just a different way of writing the coordinates of your ds vector. And you got to make sure to remember which way they go, right? It's dy dz, dz dx, dx dy, in that order, written just so. And having noticed that, then these integrands, PQR, are just the coordinates of the vector field that you're talking about the flux of. So when you see something written in this notation, think to yourself, okay, look, coordinate surface integral notation is just a clunky version of a flux integral. And the vector field, you can read straight off of what are the integrands in these coordinate surface integrals. Okay. All right. Moving along. Okay, we're done with chapter 5. We're moving on to chapter 6. Chapter 6 is a lot of really beautiful things happen in chapter 6. I always look forward to this time in the semester. It is challenging, right? There's a bunch of ideas that all kind of connect together in really fascinating ways. We're going to be able to prove some shocking results in here. Well, I say prove. We're going to see some shocking results. We're not really going to prove anything in this chapter. So the first thing I want to do is give you a little bit of a perspective on how I'm going to approach this material. I'm going to do something different than a lot of books do. One approach to this course is to give you all of the details, and it's just not realistic. This is pretty inaccessible to talk about the big theorems that are really at work here. There's something called a generalized Stokes theorem. And there's a theorem called the de Rham cohomology theorem. And this is heavy, hardcore. This is rough stuff, right? We cannot do this in Math 212. But if I was going to give you the complete picture, if I wanted you to know everything that there is to know about the topics that we're going to be talking about in Chapter 6, I would have to tell you these things, and that's just not realistic. Okay. What we're going to be seeing in this chapter, we're not going to be seeing the full generalized Stokes' theorem. We're going to be seeing a bunch of special cases. We're going to be seeing, I guess, depending on how you look at it, 6 different special cases of Stokes' general theorem. Okay. So, a point of view that can be given on how to cover this material is to present 6 independent, standalone, disconnected theorems. And that's it. Right? And you can do that. A lot of textbooks do this. A lot of textbooks say, well, here's this one theorem. It's called the Gauss's divergence theorem. Here's another one. It's called the fundamental theorem of line integrals. And they're all separate theorems. And that works, but it's really kind of disappointing because they're not separate theorems. They're not disconnected from each other. They are very closely connected to each other because they are all special cases of a single theorem. Right? These are not separate things. They're just intimately connected to each other. Likewise, the de Rham cohomology stuff. There's a bunch of different independent facts that I could list, but they're not independent. They are all related to each other. Right? So, does the instructor tell you the whole story and completely snow you? Or does the instructor tell you just these self-contained individual stories and then leave out a huge amount of really useful information? So what I'm going to do is kind of a compromise, sort of halfway in between these two approaches, and that is my compromise approach is to I'm going to set up a bunch of sloppy language. And I'm going to not define anything rigorously in this chapter, right? This isn't the context for that, Math 212. And I'm going to set up some loose language and a suggestive framework, I'm going to call it, right? That will allow us to, I'm going to say, see a bunch of the analogies and connections between the various special case theorems that, like I was just alluding to. We're going to kind of get the vibe of it, but I'm going to leave out all the ugly, nasty, sophisticated, hardcore, abstract details. Right? So a lot of what you're going to see here in Chapter 6 is you could naturally respond by, but why are we doing that? And my answer is going to be, trust me, yeah. Because if we do it this way, stuff's going to work out wonderfully. Roughly speaking. Okay. All right. So yeah, it's a weird situation. But anyway, some really cool stuff comes out of this. All right. So here's the first, hand wavy assertion that I'm going to make. Here's a bunch of objects that we're going to consider in chapter 6. You'll notice that there's 3 different contexts here. There's R1, there's R2, and there's R3. Notice that in R1 we're going to talk about intervals and we're going to talk about points. In R2 we're going to talk about 2-dimensional regions, 1-dimensional curves, 0-dimensional points. Right? In R3 we're going to talk about 3-dimensional solids, 2-dimensional surfaces, 1-dimensional curves, and 0-dimensional points. Okay, so these are what I'm going to call our domains, these various domains that we're going to talk. We're going to do certain things on these domains. Okay, what are we going to do on these domains? We're going to do various kinds of integrals, roughly. I'm going to call it, in the book I call them evaluations, which probably an unnecessary dance around. But roughly speaking, various kinds of integrals. And I'm just going to tell you what they are. Why these are the integrals that we're going to consider. Because these are the various special cases of what integrals of differential forms looks like. Don't worry about the details. I can't give you those details. So think of it this way. We're going to choose certain objects to consider because if we do, things are going to work out in wonderful ways. So on 3-dimensional solids in R3, we're going to be looking at triple integrals. On 2-dimensional surfaces in R3, we're going to be looking at vector surface integrals, not scalar surface integrals. Scalar surface integrals won't have squat to do with this conversation. Why? Because differential forms say so, and so for reasons that I can't justify here, but again, take my word for it, the objects of really strong interest in this conversation, vector surface integrals. Likewise, on curves, vector line integrals. On 2-dimensional regions, double integrals, plain old good old double integrals. Vector line integrals on curves. On intervals, good old Cap 1 single variable integrals. On the points, so this is why I didn't really want to call these all integrals, because I don't know, I'm going to say evaluation. By evaluation, I mean if you give me a domain and if you give me an integrand, that you can smash them together and out comes an answer, some value. So I call that an evaluation. If you give me a domain and an integrand, you can do the triple integral and you get a number. Likewise for all these other integrals we've talked about. And here's the thing, if you give me a point and if you give me a function, I can take the point and plug it into the function and out comes a number. So it's kind of like an integral in a way, in that sense. And you can make that precise in ways that we don't need to worry about. But anyway, so these are the kinds of evaluations that we're going to be talking about, because that's how the story goes. Okay. I need to talk about orientations. Now, y'all remember orientations, at least in certain contexts. We've talked about an orientation on a curve. We've talked about an orientation on a surface. And in both of those cases, orientations, I mean, they're different in those contexts, but in both cases, an orientation is a convention regarding sign. Right, so let me just remind you, if you have a curve, right, there's 2 different ways that you can go along this curve. So you can say I'm going to say, oriented that way, for example. That says which way to go in the computation of the vector line integral, and you get the vector line integral gets some certain value. On the other hand, if you were to go, change color. If you were to go the opposite direction, you'd get a different value, but more to the point, in going the opposite direction, you would get exactly the negative value. Remember we talked about, if you go two different directions along the same curve, same vector field, vector line integral just gets a minus sign. So the orientation, we thought of the orientation in a geometric way, and that's very appealing, and that's I'm not trashing that. It's a good way to think about orientations on curves. Think about it as tangent vectors. Right? Conventions aren't tangent vectors. But you can also think of it as, look, there's this one thing, there's this line integral, and whether I pick the blue, the purple or the green orientation, it just tells you whether you do or don't get a minus sign in some sense, right? So it's a convention regarding sign. I'd say further in this case, an orientation on a curve is a convention regarding sign in vector line integrals that can be thought of in a geometric way. Yeah, sure. But it's a convention regarding sign more fundamentally. So likewise with flux integrals, and we talked about this a couple days ago, if you have a surface, right, there's two different orientations that you could talk about. There's the sort of, that orientation on the surface. And then there's the, at any given point, you could be going the opposite direction. So on this purple surface, there's two different orientations. There's the blue one and the green one. And you can think of them geometrically, and that's nice. And you can think of, the fluid flowing different directions, or think of it geometrically however you'd like. The point is, the two vector surface integrals that you get, depending on what these orientations are, you get exact negatives of each other. So orientations are a convention. It's a choice. Which one do you want? And it's a convention, the choice of which tells you whether you do or don't get a minus sign, roughly speaking. Right? So it's another convention regarding sign. Convention regarding sign. Asterisk, which, yes, also has a geometric picture. Okay. So we're going to talk about some more orientations now. These new orientations I'm going to talk about just don't have a geometric picture. They're just conventions. End of story. They're algebraic conventions. Right? So here's the choices I'm going to talk about. Let's talk about what does it mean to have an oriented point. And this is going to seem silly. What do you mean a orientation on a point? A point just sits there. There's no direction along a point. Right? We made fun of that concept in chapter 1. Points just sit there. They don't have a direction. Right? There's no direction through a point. They just sit there. Right? Nevertheless, we're going to talk about a convention, two different possible choices that could be made. We're going to talk about a positively oriented point X versus a negatively oriented point X. And what I mean by the positive versus negative is, well, if it's a positive oriented, then you evaluate normally. Namely, you multiply by positive 1. And if you have a negative orientation on your point, then just like taking an opposite orientation on a line integral, just like taking an opposite orientation on a surface integral, the negative orientation on a point just means that when you evaluate into a function, just multiply by negative. Multiply by negative. Opposite orientation gives opposite value. This seems like a weird thing to do, and again, you might be thinking to yourself, but what does it mean geometrically? Nothing. It's an algebraic convention, ends up being really useful in what we're about to do. Likewise, an interval in a single variable calculus integral. Well, minus a negative oriented interval just means you get a minus sign. By the way, here's one that I suppose you could think of this geometrically. A negatively oriented interval, if you want to think of it as, instead of going from A to B, if you want to think of it as just going the other way from B to A, whatever that means. notice you would still get minus sign. Okay, what is a positively oriented region in a double integral? Same deal. Positively oriented just means compute the double integral and then multiply by positive 1. A negatively oriented two-dimensional region just means that when you do an integral over that negatively oriented region, you have to stick a minus sign. You have to multiply by the orientation by minus 1 after you do the integral. Okay. Likewise for tripling. Okay, so in all these cases, notice that the orientation is just a convention about what you do with signs in an integral. Okay. So, yeah, in general, a negative, when you reverse the orientation on any domain, you get the negative of the otherwise value of the integral. So you can talk about a negatively oriented, if a curve C is an oriented curve, you can talk about the negative orientation on that curve, and that means the orientation going the other way. Okay, let's talk about boundaries. What do we mean by the word boundary? Whoops, what did I just do? Oh, that's weird. Okay, boundary. I gotta find this thing not working. Oh, you know what? I just remembered. Okay, I have to change. There's a little. Let me just check out for a moment here. I'm pretty sure my recording's still going here. Yeah. Okay. Sorry about this. I forgot I have to change my file. Let me open up the other file. Chapter 6. Here it is. Use chapter 6. The program that I use here, it has some weird features that makes it not work very well after I get a certain distance into the file. Okay, so what do we mean by boundaries? It's kind of exactly what you expect. If you have an interval, the boundary just means it means these 2 points, the end points. If the edge, if you will, where does your set kind of end? So no big deal. Boundary usually means pretty much exactly what you think it does. Where it gets a little weird is the conventions on the orientations. And we're going to make some choices here. Again, they're going to seem arbitrary. These are arbitrary choices that actually come very naturally from more sophisticated ideas that we can't talk about in Math 212. So again, I apologize for the seemingly arbitrary choices, but they're actually not arbitrary. Okay, so here's the seemingly arbitrary choices. If you have an interval, by the way, a positively oriented interval on the x-axis, the boundary consists of 2 points A and B. Yes, okay, but oriented how? Are these positively oriented? Are they negatively oriented? The choice is that the starting point is always negatively oriented, and the ending point is always positively oriented. We make this as a choice because if we do, then great things happen. Again, all we're doing is making a definition of what we mean by this word boundary here. All right? Everybody on board? This is a convention that we're going to make. Etc. For other cases. What if I have a curve? All right? So some curve in space. There's a curve. Now wait a second. Specifically an oriented curve. And so let's say I'm talking about a curve oriented that way. So a curve oriented, let's see, what would you call this? You could call this oriented to the left. You could call it oriented counterclockwise. Those both kind of vaguely suggest, right, the same idea. Okay, but here's the convention. It's an arbitrary convention. It comes from more sophisticated ideas. Wherever you start, negatively oriented, and wherever you end, positively oriented. That's the rule. It's going to make sure to remember the rule. Yes, it's arbitrary, but that's the convention. Planet Earth does it this way. Okay. All right, here's a harder one. Suppose you have a two-dimensional region in R2. Solid two-dimensional region there. So when I say boundary, what do we mean by boundary? Well, no surprise, boundary means the boundary. I mean, it's where the solid ends, right? I mean, it's exactly what you think. It's these three curves. Those three curves are the boundary of that region. If the region represented property that you own, the boundary is where you put the fence, right? Okay, but question, what about orientation? So here's the convention. If this is a positively oriented region, there is a convention for what orientations you put on the boundary curves. There's three boundary curves here. Which way do you go? Do you always go counterclockwise, or do you always go to the left, or what? There's a choice. So here's the choice. This is commonly misstated. A lot of people will tell you that, oh yeah, you always go counterclockwise. That's not right. You don't always go counterclockwise. You go counterclockwise around the outside piece of the boundary, yes. But more generally, what you do is you always go in such a direction that as you walk in that direction around the boundary, so here, that's me, right? So I'm walking along the boundary that way. As you walk around the boundary, the region whose boundary you're walking along is on your left. That's the rule. Okay, so as you're walking along the boundary, the region's on your left, and emptiness is on your right. Okay, so notice that has me going counterclockwise around the outside, but notice that has me going. So here's a smaller little me there. I have to go that way on this sort of inside boundary. I have to go that way so that the region is on my left, and that has me going around clockwise, not counterclockwise. Everybody see? Any questions about that? So a nice, easy way to remember this is as long as your region doesn't have any holes in it, right? As long as your region is simple, right? Just it's a lump, right? Then yeah, it's counterclockwise. But if there are holes cut out of it, then you have to think about which way am I going, and the region's on my which side, and think it through very carefully. And the interior pieces will always be on the right. I mean, it'll always be clockwise. Okay, so that's the rule there. What about if you have a solid? You have a solid three-dimensional thing in R3, a solid lump. Again, this is commonly misstated. It's commonly misstated that you always go outward. That's not always the case. But if you have a simple, just a lump kind of a thing, again, it's always outward. That's an easy little rule to remember. What's always true is that wherever you are on the boundary, there's two different directions you can go perpendicular to the boundary. So in this case, there's that and there's that. Two different ways you can go. Of these two different ways that you can go perpendicular to the boundary surface, one of them goes into the solid, one of them goes away from the solid. The correct orientation, the convention for the correct orientation on the boundary surface is to go in the direction away from the solid. It's totally arbitrary. Why couldn't we go into the solid? Look, maybe on Mars they go into the solid. I don't know how they do math on Mars, but on planet Earth we go away from the solid. It's an arbitrary convention. It kind of doesn't matter, but this is the convention that we work with. Okay, so away from the solid. Well, now let me argue then that consider now if our solid has a hole in it. Right? If our solid is hollow, maybe our solid isn't a baseball. Maybe our solid is a racquetball. Think about that point on the boundary. That is a point on the boundary. The boundary is this sort of the inner surface, if you will, of the racquetball, right? And notice that away from the solid is not outward. On the inner surface, away from the solid, and here's the rubber. There's rubber, there's not rubber. Right? Away from the rubber is actually inward. Does that make sense? So be careful with that convention as well. Here's the hard one. Suppose you have a surface, and there's different ways to think about this. I'm just going to skip to the one I think is the most convenient. Here's a surface. Now, careful. This is not just a surface. I need to give you an oriented surface. I've got to tell you which way is this surface oriented. I'm going to give you a normal vector. That normal vector now tells you what orientation we have on our surface. So which direction this surface is. What's the correct direction through this surface? Okay, so what's the boundary? Well, the boundary, it's not hard to, the boundary consists of, it's curved, right? It's the edge of the surface. Where does the ant get confused? Well, the ant's walking along the surface and he gets there's nothing over there, he doesn't know where to put his feet. That's the boundary, right? It's the edge. So which direction, though, is the proper orientation? Is it that way along the edge, or is it that way along the edge? The rule, again, there's different ways to think about it. Here's the way I like to do it. Right hand. Apologies to the left-handed. Take one of your normal vectors near the edge, not on the edge. Near, but not on the edge. Point your thumb in the direction of the normal vector. Look at which way the fingers of your right hand are curling around. Notice that creates what I would like to call a swirl. Right? That swirl will sideswipe up against the boundary in the correct direction. So if you have an orientation on your surface, that orientation is a normal vector. The normal vector, you can put your thumb. Having to put your thumb that way, your fingers want to bend a certain way. That tells you which way to go around the boundary. Now, there's different ways to do this. One is to think of yourself as a little person. Again, here's me. And you could say, well, I walk in the direction such that, the region's on my left. But then the question comes up, how am I oriented? How do I know that I'm not oriented like that? Okay, so the rule is, no big deal. The rule is that, you always orient yourself as suggested by a normal vector. So that kind of resolves that problem, right? And so again, here I am. I can say, okay, oriented in such a way that my head's in the direction of the normal vector, walk in such a way that the region's on my left. That works. It's fine. Except, and until you get to a situation like this, and okay, let's see, how do you figure out what's the correct orientation, along in this part of the curve here, and you're like, okay, wait a second, here's me. My normal vector is that way. So here's me. Totally. You're going to go crazy trying to make sense out of what would this thing look like if I were, I've got to orient myself sideways or upside down or what have you. It's super confusing, right? But it's just the world's easiest thing in the world to do to say, downward, okay, thumb in the downward direction. Look at the way that your fingers are going, right? And no big deal. That the side swipe is like that. Right? And so that side swipes in this direction around the boundary curve. and also in this direction around that piece of the bounded curve. Sorry?
That's right. Again, it's not easy going in that direction because it simply opposes the direction of the side, right?
I'm sorry, one more time.
The direction of the like the edge is like that because we said it opposes the direction of the pole.
So the convention is that when you have a normal vector, right, and you do with your thumb and your right hand and your fingers, right, and you look at which way the swirl is, and that swirl side swipes that way, right, on that side, but on this side, it side swipes that way. Does that make sense? Yeah. And notice that this is a consistent story. You say, well, what about if I went to the other side? Wouldn't it be backwards? But no, if you come over here, the normal vector is like that. The swirl is again like that. It side swipes the same way. And so, on this inner piece, the orientation is like that.
But then, like, the holes, which direction do they take? Like, if you do like a thumb rule, shouldn't the holes take the thumb rule, like the thumb rule's direction, or is it just the edge that takes that?
I'm not following your question.
It's like with the thumb rule, like the right hand rule.
So the right hand rule is you got to follow the right hand rule explicitly though. The right hand rule says find a point on your surface, critically on your surface, right, and put your thumb in the direction of the normal vector, blah blah blah. And so that has you going around this way. You may be thinking in terms of, well, what if I look at this point? That's not a point on my surface. See what I'm saying? And so you can't say, oh, I want to think about these points near that piece of curve and do this, and then it would seem backwards, right? But those aren't points on my surface. Yeah. Right. Yeah. Or did you have one?
Yeah.
Yeah.
If there had been like a circle inside of our empty hole there, would it go in the same direction?
If there'd been what now?
A circle, another surface inside the empty circle.
Oh, okay. So you're saying that we have. So here's our existing thing, and you're saying furthermore inside of there, there's an. Oh, my little. My pen is too thick. Let's make it thinner. There's another little thing inside of there. Well, so that's a disconnected. It's a disconnected piece, and we have to be told what the orientation is on that piece of surface. And if the orientation on that piece of surface were, if it were like that, then thumb, swirl, etc. But there's no law that says it has to be. I mean, because it is disconnected. So there's no. I mean, I can say that this orientation sort of necessitates, just by consistency, that I have that orientation there, and just again by consistency, it sort of has to. On the entire connected piece there, you tell me one normal vector, and consistency tells me what it has to be everywhere else. But on your hypothetical piece, and being disconnected, it would have to be told. Yeah. Okay, we're actually out of time. I went 3 minutes over. Sorry about that, but that was y'all's fault with questions. So anyway, we'll call it a day, and we'll pick up here on next time.